Hello dear students, welcome you all. In this lecture we are going to drive Maxwell relations, right? So uh, Maxwell relations, as I told you, that these are the relations which are very important part of the thermodynamics, right? Maxwell relations are basically four equations, right? uh, which are derived from four thermodynamic potentials, right? Uh, we will start from the relation number one, first Maxwell relation, right? And for it, we will make the use of first thermodynamic potential, that was internal energy U. We have seen that U is a function of S and B. Clear? So if we take the total differential of U, then from the theory of derivatives, we know du should be equal to curly U upon curly S B into ds plus curly U upon curly B S into dB. Clear? So this is this total derivative of U is according to the theory of derivatives. We have learned it in the mathematics. Now we also know that the differential form of this thermodynamic potential, that is internal energy, du is equal to Tds minus Pdb. So if I say this is equation number 1 and this is equation number 2, then when we will compare these two equations, you can see here that uh, curly U upon curly S B is equal to T, and curly U upon curly B S is equal to minus P. So this is when we compare 1 and 2. Clear? Uh, we also know that as du is a perfect or exact differential. It is a perfect differential or exact differential. What is a perfect differential or exact differential? We know any function is set to a perfect differential or exact differential if its value in any process depend only on the initial position and final position. It does not depend upon the path followed. So all the four thermodynamic potentials, internal energy U, enthalpy H, gives free energy G, and Helmholtz free energy F. All they are state functions, or they are perfect differentials or exact differential, because their value in any process depend only on the initial and final position of the process, right? It does not depend upon the path followed. So if du is an exact differential, then it must obey Euler's equation, right? Euler's equation is it must away curly upon curly s into curly u upon curly b at s should be equal to curly upon curly b into curly u upon curly s b, right? This is the condition of Euler's equation. If a function is perfect differential, exact differential, or a state function, then it must satisfy this, right? So if we compare this equation with equation number 2, then we can put the value of curly u upon curly v and curly u upon curly s from this equation. Clear? Not equation number 2, but it was equation number 3. Clear? From 3. So what you will get when you put the value, you will get, it will become curly u upon curly v is curly t upon curly s. Clear? Now it is not s, but it is with respect to b. That should be equal to curly u upon curly s is equal to curly u upon curly v. Oh, sorry, it was curly u upon curly b. It was minus p here. So here we have to use minus p. And minus that should be equal to curly u upon curly s is equal to t. So curly t upon curly b and it is s. Clear? So this equation becomes curly p upon curly s with respect to b, that should be equal to curly t upon curly v with respect to s. This equation, this relation is called Maxwell's first relation. First relation. Clear? Yeah, first equation. Right? Now we will go to the equation number 2. So we can revise this from where we started. We started from the thermodynamic potential U, internal energy, right? We took the total derivative, then we used the differential form of this thermodynamic potential. We compared these two, then we found equation number 3, and then as U is a exact or perfect differential, so it must follow Euler equation, right? So after writing Euler equation and comparing, we found this relation, which is the Maxwell's first relation, yeah, Maxwell's first equation, right? Now I'm coming to the Maxwell's second equation, yeah, second relation. Right? Maxwell second relation. So we will derive Maxwell second relation from Helmholtz free energy F. Clear? We know F was a function of volume and temperature. Clear? F was a function of volume and temperature. Helmholtz free energy is a function of this. Now, again, I'm taking the total derivative, that is df is equal to curly f upon curly b t db plus curly f upon curly t b dt. Clear? So this is from the theory of derivatives. We also know what is the differential form of f. So f was equal to df was equal to minus p db minus s dt. Clear? So this was the differential form of this second thermodynamic potential, Helmholtz free energy. Clear? So if we compare these two equations, this equation number 1 and equation number 2, then what we will found? We will found curly F upon curly B T is equal to minus P, and curly F upon curly T B is equal to minus S. You can say this is equation number 3, right? Again, the same thing, that as df is the exact differential, so it must obey the Euler's equation, that is curly upon curly B curly F upon curly T B must be equal to curly upon curly T curly F upon curly B T. Clear? This is equation number 4. Clear? For this particular relation, right? So you can now use equation number 3 in equation number 4. So you will get curly upon curly B. Now what is curly F upon curly T? It is minus S. Clear? Now it was with respect to B, so it will become with respect to now T. Clear? Should be equal to curly upon curly T. So what is the value of curly F upon curly B? Curly F upon curly B is minus P. So minus P, and it was with respect to B. So minus minus got cancelled, and we are left with curly S upon curly B with respect to T, right, must be equal to curly P upon curly T with respect to B. Clear? So this is curly S upon curly V with respect to T must be equal to curly P upon curly T with respect to V. This is Maxwell's second equation. Second equation, the second relation. Clear? So this is the second relation. Now I'm coming to the third one. So third one is it is driven from enthalpy H. Clear? We know H was a function of S and P, entropy and pressure. Clear? So again, from the theory of total derivatives, the total derivative dH should be equal to curly H upon curly S P ds plus curly H upon curly P S d P. Clear? So when you take the differential form of this function, this thermodynamic function, TdS plus B dP. Clear? So if you compare this equation number 1, again in this case equation number 2, you compare these two, then you will find curly H upon curly S P is equal to T. Clear? Similarly, curly H upon curly P S is equal to B. Clear? So this is the comparison we got, and let it is question number 3. So again, as I told you in the beginning, that DH is also a exact differential. Exact, right? So it must obey Euler's equation, that curly upon curly P into curly H upon curly S P must be equal to curly upon curly S into curly H upon curly P, right? S. So when you will compare this equation number 4 with equation number 3, and we put the value of curly H upon curly S, you will get curly T upon curly P. Now the derivative will be this, and it is keeping S constant, and it is curly B upon curly S, right? Because the term inside the bracket is equal to B. Clear? And it is with respect to P, right? So curly T upon curly P with respect to S, curly B upon curly S at constant P, that is Maxwell's third relation. Right? Now let's come to the relation number 4. Clear? Maxwell fourth relation. So Maxwell's fourth relation, right? So we will derive Maxwell force relation from Gibbs free energy G. We know G is a function of P and T, right? So the total derivative dg must be equal to curly G upon curly P constant T dp plus curly G upon curly T constant P dt. Clear? So this is let equation number 1 in this case, and we know the differential form of this thermodynamic potential dg is equal to V dp minus S dt. Clear? So when you will compare these, you will get this is equal to this, and this is equal to this. So you will get curly Z you will get curly Z upon curly P T, that is equal to B, and curly Z upon curly T P is equal to minus S. Clear? That this is equation number 3. It was equation number 2. So when you will take dg again as the exact differential, right? Then we know it should follow the Euler's equation, right? So Euler equation is what? Curly upon curly T curly G upon curly P at constant t, that should be equal to curly upon curly p into curly z upon curly t p. This is the Euler's condition, that exact differential Euler equation that must be followed, right? So when this is equation number 4. So when you will put these values, curly z upon curly v, here b will come here, and minus s will come here. Clear? So when you will simplify it, so when you will put the values here, you will get it will become b, and it will become s minus. So it will be with respect to p, and it will be with respect to t. Clear? So curly v upon curly t at constant pressure, that should be equal to minus curly s upon curly p at constant temperature, right? So this equation is called Maxwell's fourth relation, right? So these are the four Maxwell relations, yeah, we can say equations that we have derived here. These are very, very important from the perspective of examination, as well as from the perspective of next topics that are going to be discussed here in this chapter, right? Because now in the coming articles, we will make the applications of these Maxwell relations. Now, I'm going to tell you that what is the trick to remember these four Maxwell thermodynamic relations, right? So there is a trick by using which you can remember these four thermodynamic relations. So trick is, you have to first of all write P, V, T, S. Clear? So for the first thermodynamic relation, Maxwell thermodynamic relation, you will start from T. You will write is T, P, S, and B in this way. Clear? You are going in this way. Clear? Now then you will take this. So it will become curly T upon curly B. Clear? S, that is equal to curly P upon curly S with respect to B. So how I did it? Simply by taking curly here. So it becomes curly T upon curly V S, curly P upon curly S B. Negative sign is there because we have going in the direction opposite to the direction of the clock. Anti-clockwise movement is there. So this is first Maxwell relation. So this is the trick to remember it. Similarly, if we want to remember the second equation, then again same thing, P, B, T, S. So what we will do now, we will move from here in this way, right? So what it become? S, P, T, B. Clear? S, B, S, P, T, B. Clear? So what it become? It becomes curly, 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 curly. So here it will be clear is equal to, here it will become T, right? Here it will become B. So curly S upon curly V, that is equal to curly P upon curly T, B. So this is Maxwell's second equation. Or we can say second relation, right? Similarly, if you are going for the third one, then you have to again write this diagram. P, B T S, right? So now we will move in this way. So it will give you T B S P. Clear? So what it will become? It will become curly T upon curly P at constant S, that is equal to curly V upon curly S with respect to P. Clear? Curly T upon curly P S, curly B upon curly S P. Clear? So this is Maxwell's third relation. Clear? So now I'm coming to the next one, last one. In last one, you will go in this way. Clear? Counterclockwise again. So it will become S B T P. So what it will become? It will become curly S upon curly P should be equal to, as we are moving counterclockwise, it is negative curly B upon curly T and P, and it is T, right? So curly B upon curly T must be equal to curly S upon curly P. Clear? So this is Maxwell's fourth relation. Clear? So this is the way of driving these four equations and remembering these four equations from the point of view of examination. This is the best trick for remembering these four equations. You have simply write this P, B, T, S. This is first, this is second, this is third, this is fourth. First and fourth are negative signs because counterclockwise movement is there, and these two are a positive. Clear? So this is all about the Maxwell relations or Maxwell equations, which we have derived by making the use of thermodynamic potentials and their derivatives, right? So this is all about it. Thank you.